Welcome. This screencast is the third in a series where we will look at transforming the sine and cosine functions. In our previous study of transformations, we saw how vertical stretches impact the amplitude and range of sinusoidal functions. In this video, we introduce a new transformation, horizontal scaling. We can think of horizontal scaling as a horizontal stretch. In what follows, we will determine how horizontal scaling impacts the graphs of the sine and cosine functions. While we will focus on horizontal stretches of the sine and cosine functions, it is important to note that horizontal scaling follows the same principles for any function we choose. Horizontal scaling occurs when the input is being scaled by a factor of k. For example, writing y equals the sine of kt communicates that the sine function is being horizontally scaled. Let's look at these various graphs of y equals the sine of kt to get an intuitive sense of how the value of k affects the graph of y equals the sine of t. First, we will identify the value of k, the effect on the graph, and the period. Then we will look for a relationship between k and the period. The first graph is the parent function y equals sine of t. So k equals 1 and the period is 2 pi. The next graph, y equals the sine of 2t, is graphed in black and has a k value of 2. We notice that y equals the sine of 2t is a horizontal compression of y equals the sine of t toward the y-axis, and that the period is pi. Next, y equals the sine of 3t, also graphed in black, has a k value of 3. We notice that y equals the sine of 3t is a horizontal compression of y equals the sine of t toward the y-axis, and that the period is 2 pi over 3. Next, y equals the sine of 4t has a k value of 4, and again we notice that the sine of 4t is a horizontal compression of y equals the sine of t toward the y-axis, and now the period is pi over 2. Lastly, y equals the sine of 1/2 t has a k value of 1/2. We notice that y equals the sine of 1/2 t is a horizontal stretch of y equals the sine of t away from the y-axis, and that the period is 4 pi. Pause the video and see if you can determine the relationship between the k value and the period that we found in each of these graphs. Alright, so perhaps you noticed that in all of these cases, the period could be found by dividing 2 pi by the k value. For example, when y equals the sine of 2t, 2 pi divided by the k value of 2 results in the period of the function pi. Similarly, for y equals the sine of 3t, 2 pi divided by the k value of 3 results in the period 2 pi over 3. And for y equals the sine of 4t, we see that 2 pi divided by 4 equals pi over 2, which was the period of y equals the sine of 4t. Lastly, when y equals the sine of 1/2 t, 2 pi divided by 1/2 is equivalent to 2 pi times 2, which equals 4 pi. Based on the patterns in our observations, we conclude that given y equals the sine of kt, we can determine the period by 2 pi divided by k. In fact, our informal observations are correct, and we can say that for any constant k greater than 0, the period of the functions sine of kt and cosine of kt is p equals 2 pi over k. Further, we also observed that if 0 is less than k less than 1, in other words, k is between 0 and 1, the graph is a horizontal stretch of f away from the y-axis. And if k is greater than 1, the graph is a horizontal compression toward the y-axis. As we have seen, horizontal scaling enables us to generate circular functions with any period we desire. As we think about using transformations of the sine and cosine functions to model different phenomena, it is apparent that we will need to generate functions with different periods. For instance, if a Ferris wheel makes 1 revolution every 5 minutes, we'd want the period of the function that models the height of one car as a function of time to be p equals 5. This leads to the need for us to be able to find the value of k given a desired period. In other words, we need to find the value of k given the period. We can do this by solving our equation p equals 2 pi over k for k. First, we multiply both sides by k, resulting in pk equals 2 pi, and then divide both sides by p. So we find that k equals 2 pi divided by the period. If we know the desired period, we can therefore find k by the rule k equals 2 pi divided by the period. Let's look at a final example where we put together everything we've learned about transformations. Let h of t equal the negative sine of the quantity pi over 2 times the quantity t plus 1 minus 2. Without consulting a graph, determine each of the following. Pause the video and try this on your own. Okay, so we can identify that the k value is pi over 2, and we know the period equals 2 pi over k. Simplifying, we get 2 pi times the reciprocal 2 over pi, which equals 4, making the period 4. The a value is negative 1, so the amplitude is 1. The graph has been shifted down 2, so the midline is y equals negative 2. And since the midline is y equals negative 2 and the amplitude is 1, the range will be negative 3, comma negative 1. Because of the t plus 1, the horizontal shift is left 1 unit. Finally, horizontal shifts cause the t value of the anchor point to be at negative 1, and since the function's starting point is on its midline, the output value of the anchor point is negative 2. In conclusion, multiplying the cosine and sine functions by a factor of a applies a vertical stretch or reflection across the x-axis, and a vertical stretch determines the amplitude of the transformed function. Adding the real number c to the cosine or sine functions applies a vertical shift, and that determines the midline of the transformed function. By starting at the midline y equals c and subtracting the amplitude, we get the lower value of the range, and by adding the amplitude, we get the upper value for the range. The real number b applies a horizontal shift to the sine or cosine function. The anchor point for the cosine function has a t value that is equal in value and direction of the horizontal shift, and the output is determined by adding the amplitude to the midline. While for the sine function, the anchor point has a t value that is also equal in value and direction of the horizontal shift, and the output is determined by the location of the midline. Lastly, the real number k applies a horizontal scaling, and the period equals 2 pi over k.